welcome everybody. Today's session is organized by the ESIT program. ESIT stands for Ethics of Socially Disruptive Technologies, a large research program in the Netherlands, focusing on disruption of social and conceptual disruption caused by technologies. And on today's sessions, as the title said of the session, we focus on what's called conceptual design. And just to explain this, what we're going to do is we're going to talk about how new value concepts, so we focus on values, how new value concept might be designed or developed in response to challenges faced by emerging technologies. But also we will discuss how such newly designed concepts can play a role in the design of what you might call responsible technology. We will be using in some of the talks the concept of meaningful human control as an example of a new concept that has been proposed in response to challenges faced by artificial intelligence. And we will show in the talks how this concept might affect the design of AI. So to give an overview, what we will do, we will start with 4 talks. And after those 4 talks, we hope ample room for questions and discussion. So I will kick off. Just to inform you, I'm Ivo van der Poel. I'm a professor in ethics and technology at TU Delft and part of the ESIT program. So I will be talking about an approach that's called design for values. That's an approach that aims at developing more responsible technologies by taking more value seriously into account. Then in the next talk, Herman Veluwenkamp from the University of Groningen will be talking about design for values and conceptual engineering. And he will argue that if we want to do design for values, we need conceptual engineering and we might need the development of new concepts. Then Giulio Mecacci takes over from the Donders Institute, also in the Netherlands. And he will be introducing this concept of meaningful human control over AI systems. And we end with a talk by Luciano Siebert, who is also from my university, TU Delft. But he is not in the philosophy group where I am, but in the computer science group. And Luciano will explain how this concept of meaningful human control can be effective for designing AI systems and what it means. And then we, in a sense, full circle. So I will be talking a little bit about this idea of design for values. So what is meant with that? So design for values is you might describe it as a systematic attempt to include values of more importance in design. So it is about how do we take into account values that are more important in the design of new technologies. There's now a lot of talk about, some people also talk about these things like ethics by design, and it is part of these types of approaches. You might say the general aims of design for values are often formulated as being twofold. So on the one hand, the idea is that if you design for values, the technologies you design might be easily socially accepted. So stakeholders might be willing to use these technologies because they see their values being respected. But at least as important, or maybe I would even say more important, is also that it leads to design that you might call morally acceptable. So that from a moral point of view are good technologies or responsible technologies. And that, of course, depends on whether the technology respects moral values. And design for values is a kind of methodology or a kind of approach that tries to do it in a systematic way. So what does that entail? One thing to say is, and this is comes from Batja Friedman, who did a lot of work on what's called value-sensitive design. And she argues, and I think rightfully so, if you do this kind of approaches, you typically need to combine 3 types of investigations, what we call empirical, conceptual, on which the focus will be today, and technical engineering, about which we will also say something. So the empirical is about you should do research. What are the relevant stakeholders? What are values that are at play here? The conceptual is about the conceptualization of relevant values, something that will be kind of key topic today. Also dealing with trade-off or tensions between values. We won't be talking so much about that today. And the technical engineering is also about how do you embody these values in new technologies, on which Luciano's talk will say more. Another way of sketching the values and the design process, and this partly related to the previous, is in terms of different, say, what you might call a design cycle, which would typically start with, in the left corner above, with a kind of analysis of the context. So if you're designing a new technology, you might think of an AI app for health, for example, but that could also be something like a bridge, whatever technology. You will typically start with analyzing the context. So what are existing values and needs? What values are relevant? What are social challenges, and so on. So then you'll have a phase what I here call value identification. In there, you try to identify what values are at stake for this technology. What values should this technology be designed for? That can come from a more general list of values, but it can also be much more case-specific values. And then there is what I call the design phase, on which we will focusing most today, which is about designing of what these values mean, designing of the technology, translating values into design requirements, and we'll be saying more about that. Also dealing with conflicting values. And then you typically would have what we here call prototyping phase. So you build the technology based on these values, and you check whether they meet or address these values. And of course, this prototyping phase might show that something doesn't work, like it is supposed to, that some values are not respected, or that some values have been forgotten, and then it could be another iteration of the cycle. So one important tool that has been developed in this design for values is what has been called a values hierarchy. I did myself some work on this, and the idea of a values hierarchy, and it will be central in some of our talks, is that if you design for values, you'll have certain values, and you can associate more general norms with these values, but ultimately you can translate these into the design requirements that can guide the development of a specific technology. So if you have a value like privacy, you might have a norm like you should not collect personal data, or you might have a norm you should securely save personal data. That's a kind of general norm, and that might translate into very specific requirements for a system you're designing. So that's the idea of this values hierarchy. And I will now say a little bit more about two important things in constructing a values hierarchy, namely what I call the conceptualization of values and the specification of values. So the whole design for values methodology is more, maybe even much more than this, but that's what we focus on. So let me first say a little bit about what you might call conceptualization of values. And roughly you might define conceptualizations along these lines. If you conceptualize a value, you try to provide a definition, analysis, or description of the value that clarifies what it means and how it can be applied. So that's roughly what we mean with conceptualization. Now, oftentimes, if you in design for values, you will find that there are, from the philosophical literature, for example, different conceptualizations of a value, which have different implications for your design. So if you take as an example privacy, and you think of information systems, you roughly see three main conceptualizations in how people have talked about privacy and how to understand or conceptualize it in relation to such systems. So you see understandings of privacy in terms of confidentiality, so that personal data should remain as much as possible confidential, which means that personal data are to be kept secret or confidential. And basically, it also means, for example, if you design take a healthcare app, that you should also collect as little information as possible, because all information that you collect and store can lead to potential privacy breach. Even if you keep it secret and confidential, or you have some way that it is not accessible to everyone, of course, it can be hacked and so on. A second understanding of privacy that you often see is privacy as control. And that's often related to the idea of informed consent. And the idea here is that privacy is not necessarily means that all information about me should remain confidential, but it much more is that I am in control what data I can share with whom. Now you can imagine if you design an information system or an app or whatever, is that the technical way you build the app will be rather different if you understand privacy as control, because then you need to build structures so people can give consent to sharing data, ideally also can withdraw consent later, and that of course requires a whole kind of technical, different kind of infrastructure than if you design for confidentiality. And then a third notion of privacy that is around in the literature is privacy as contextual integrity, particularly articulated by somebody like Helen Nissenbaum. And there the rough idea is that what information can be shared depends on different, what you might call domains or spheres in society. So to put it a bit simplistic, medical data about me, it might be appropriate to share with my doctor, but it wouldn't be appropriate to deal that with to share that with my employer. And this is another notion or another conceptualization, I would call it, as privacy, which also has implications for the design of systems. So as this slide already shows, how we conceptualize values can have huge implications for how we design technologies. And I think Herman in his talk will also tell more about how conceptual engineering can come in here and play an important role. What I will do in the remainder of my talk is say a little bit about this further phase. So if you let me go back to, so if you take this values hierarchy, this conceptualization of values is still at a quite high level in this values hierarchy, but you want to go more down and you want to come to design requirements. And that's what I call here specification of values. So specification is here understood as making a value more specific so that it can guide actions and decisions in a specific context. So it really tries to think through what this value means in this context and what implications follow for actions, but also for design for the value in that particular context. Well, this is indeed. So that can be done with creating such a values hierarchy. And it is important to say that you can do that basically in two ways. So one way is to start with the values, to associate norms with these values, and then to translate it into design requirements. But in principle, you can also use the values hierarchy in a bottom-up way. So you could start with a proposed design and look at design requirements and try to reconstruct what norms or values might be behind it. The question that you then would typically ask us here is, for the sake of what, and for what purpose, you might say, for the sake of what do we have these design requirements? And then also go up from the design, from the norms, you get the norms, and from the norms you might go to the values. And that's interesting because that means that, for example, this gives engineers a tool to become more aware of what values there might be behind their designs, but it might also help them, once they realize these values, that it means that maybe in terms of design requirements, they should have more requirements to really take these values seriously. So that's roughly the idea of the values hierarchy. And so you go, the top-down process is a specification process. Important to say that's a non-deductive process because it is context dependent and it adds information about, for example, the scope of a norm, the specification of goals, specification of means. So one of the implications of this, that is a non-deductive process, is that there's usually not one way in which you can do a specification, multiple ways, but still you have, I would argue, a criterion of adequacy. The criterion of adequacy basically means, would you count meeting the lower level norms or the design requirement, would you count that as an instance of meeting the high level norm or value? Let me first go here, because then I can show how this works also a little bit, this approach. So here you see an example of a values hierarchy. This one was reconstructed from European laws about animal welfare, particular for chickens in laying hens that are kept in cages. And this reconstructs the law as it existed in around the 1980s, 1990s. And what you see in this is that, so you have the value of animal welfare that has been translated in a number of norms, basically from biologists that looked at animal welfare that says, well, these norms need to be met in order for something to count as animal welfare. That includes norms like enough living space, presence of laying nest, litter, perches. And then you see that some of these have been translated in what are here called design requirements in the European law. And you see a requirement about how many square centimeters floor per hen, how many feeding food per bird. So very specific quantitative requirements. But it's interesting if you now ask, I said the adequacy criterion for specification is whether if you meet the lower level requirements, do you then meet the higher level value? And if you ask this question here, I think it is quite clear, or at least on some reflection, that the answer is no. So there's 450 square centimeters, just for your imagination, that's less than an A4. But one of the things you here see is that some of the norms have not been translated in design requirements at all. So here it seems that this law that is meant to effectuate animal welfare in the design of battery cases actually does not make a sufficient specification, because you would, I think, on reflection, you would say that if you meet the design requirements, you still not have a system that meets the requirements of animal welfare. So the design the value hierarchy is a tool to see these things. Let me say indeed a little bit about the bottom going up relation. That's called for the sake of. And so the idea is that the higher level elements in the value hierarchy provide reasons for striving for the lower level elements. That's an anti-symmetrical relation. And you might say, interestingly, that if you do this up until the top, at the top you end up with intrinsic values that are done for their own sake. So I already explained this, I think. So let me summarize what I've been talking about before we go to the next speaker. So I've been saying design for values is an approach for integrating values of more importance in technological design, trying to do so in a systematic way. It consists of a number of tools and design cycle. One of the important activities in design for values is what you might call the conceptualization and specification of values, and we focus certainly on the conceptualization of the next talk. And indeed, this conceptualization of values might require conceptual engineering, as we will see in the next presentations.
Thanks, Ivo. Thanks, MG, for organizing this. So, in my talk, I basically have two aims. So I want to build up on some of the work some of the things that Ivo has already told us. So what I want to do is want to argue that if we engage in engineering, so if we take the design for values methodology seriously, then we cannot do without conceptual engineering. So a conceptual analysis is not enough. And secondly, I want to sketch a methodology for integrating conceptual engineering with the design for values framework. And the way I would like to do that is by focusing on a specific context, a specific emerging technology. And that is the technology of autonomous systems in general, or self-driving cars in particular. And one of the values that we take to be important when we design for these technologies is control. So we take it to be important that we design these systems in a way that a human being has control over it. So there are different reasons for that. So we don't want our systems to be out of control, because then we expose harm on others. And there is some link between control and responsibility. And we think it's important if something goes wrong or if something goes right, that we can attribute responsibility, moral or legal responsibility. So what I would like to focus on a bit now is how we would construct a values hierarchy when we are designing for control. So as Ivo already indicates, so one of the first things that we do in such cases is we look at which conceptualization of control is prominent. And when we look at the engineering literature, so I mean here the car engineering manufacturing literature. So one of the conceptions that is dominant is that of operational control. So what is operational control? It is defined as follows. So an agent A has operational control over an outcome only if the agent is able to directly causally influence the outcome. So the term directly here I use without much precision. So this is supposed to be a somewhat fake notion. But the idea is that the distance in the causal chain between the agent and the outcome shouldn't be too large. They should be fairly close together. So, and this conception is explicit in the engineering literature, but I think it's also implicit in much of the literature on responsibility gaps. So when we look at the work of Robert Sparrow, for example, when he argues that autonomous systems open up responsibility gaps, he seems to be working on this notion of operational control in the background. So how does a values hierarchy look like when we use this conception of control? So when we take the top-bottom approach that Ivo mentioned, so we start with the value control here. And when we translate that into a context-sensitive norm, when we use the conception operational control, so we have a norm that says something like that there should be a human being who's able to causally influence the system. And how can we translate that furthermore into a design requirement? So I think it's rather plausible if you work on this kind of conceptualization, that there is a requirement that there should be a driver who has to touch the steering wheel every 30 seconds. So that's one way of indicating that there is a human being who is able to directly causally influence the outcome of the system. So given such a conceptualization, this design requirement is rather plausible. But not everyone has been happy with this this way of conceptualizing control. And so Johannes Himmelreich, for example, has offered a rival way conceptualization of control. And so he calls this conception a robust tracking control. And this is defined as follows. It's somewhat simplified, but it says that an agent has control over outcome O only if O tracks the directives or the commands of the agent in a way that is modally robust. So if the agent gives the command, then O occurs, and if he wouldn't have given the command, then O won't occur. So how does this look like? How does a values hierarchy look like if we use this conceptualization? So it could look like something as follows. So we start with control at the top, and the context-sensitive norm that is then that their outcome should track the outcome of the system should track the human decisions, the commands, the directives. And this isn't necessarily done by making sure that a human touches a steering wheel. So what is important here that there are mechanisms that link the decisions and the commands to certain outcomes. But these links, the causal chain can be as long as necessary. In principle, there doesn't even have to be a causal chain as long as there is this tracking relation. There's a modally robust tracking relation. So what we can see here is that the conceptualization we opt for determines the kind of car that we end up with. And this is not only the case when we talk about self-driving cars, it's also the case when we look at other technologies. So for example, when you design a social media platform for democracy, so if you want to make it democratic, and the kind of social media platform that you will end up with will depend on the way you understand democracy. So if you understand democracy as contestation, then you will build into such a platform ways to contest or to protest the outcomes of the system. But if you think of democracy more in liquid or more in direct forms, then what you will want to build into the system is ways to make the users vote on outcomes. And so the way you implement democracy really depends on how you conceptualize it. And the same holds for trustworthy AI, which is now an important concept, of course. But how you implement trustworthiness in an AI system depends on whether you understand it as a kind of epistemic reliability, or as a more in moral terms. So epistemic reliability requires you to show that it is able to operate reliably in different contexts. But if you understand trust in moral terms, then to show that it's trustworthy, you really have to show that certain values were part of the design process, that the system was designed with certain values in mind. And that's the only way to get trust, if trust is understood in this moral way. So what does this show us? So this shows that if we want to design for the proper value, if we want to design properly for a specific value, then we have to determine which conception is best in a specific context. So, and this is important to see that this is a conceptual engineering question. So, and this is not a question of conceptual analysis. So we're not asking the question whether the engineers understand control as operational control, because we kind of know that they understand it in a specific way. We also don't want to know how we understand it. So the question is, how should we understand it in this specific context? And the context is here also important, because a conception of control that is apt for regular cars and non-self-driving cars might not be apt for self-driving cars, but more on that soon. So how can conceptual engineering help here? Given that we need conceptual engineering to do this well. Conceptual engineering can help here by borrowing one of the methodologies that is prominent when doing conceptual engineering. So there's no consensus on the proper methodology, but the functionalist approach to conceptual engineering is becoming more and more popular, and it's the one that I favor as well. And on my favorite interpretation of this methodology, what we should do is when we engage in conceptual engineering, we first have to determine what the normative function of a specific concept is. So in this case, control. So we have to determine what it is that control does for us in a way that matters normatively. And that is the normative function. And then we should determine which of the rival conceptions fulfills this normative function best. And perhaps when none of the conception is apt, we should construct a new conception. So how does this work in practice? How can we combine this? What we do is we start with how we normally would create a values hierarchy. So we start with our top level concept, in this case control, and we do so until we identify a problematic concept. With problematic here I mean a concept for which there are rival conceptions, or a concept that isn't able to fulfill its function properly. So in this case we have control, because we have different rival conceptions of control. So we now should determine what the normative function of control is. So what does it do for us, which matters normatively? So one intermediate step to do this is to first determine what the current function of a concept, what the current function of the concept is. And when we do that, we try to reverse conceptually engineer the concept. So that we have different approaches in the literature that do this. And Miranda Fricker has a historical approach. Katrina Dutil-Novas and Mathieu Quelos have historical approaches. And what they all try to do is they try to identify what a concept currently does for us. But this is, of course, only an intermediate step, because what a concept does for us might be problematic. So it might have racist or sexist aspects. And we don't want to design for that. So what we should do is which aspect of the function, or how to modify the function in a way that gives us a description of the function that tells us what it does, which matters normatively, so which is normatively significant. And that's a normative function. So it would be too much to do that for the current concept. I had to do the whole process, but I think we can give a plausible function for control, normative function of control, by the following description. So I think control does two things for us that matter normatively. One, when we say that an agent has control over a system, that means that we have decreased the risk that we expose others to, right? Because there's someone who controls that, and one part of control is decreasing risk. And the second part is that it allows for appropriate responsibility attributions. Control seems to be a necessary condition for responsibility. So given this function of control, we can then look at the different conceptions that we have, in this case, operational control and tracking human control, and see whether they fulfill the conception of control in the context that we're talking about. And here the context is important, because operational control, so when we think about regular cars, operational control might be fine. And so it might be fine that if a human being is able to influence a car directly, then probably that will decrease the amount of harm we expose others to, and it also allows for responsibility attributions. But the moment we start introducing more and more autonomous systems, and we start introducing self-driving cars, this conception isn't that plausible anymore. And there are different reasons for that, but one reason for this is that when we think about fully autonomous systems, so this is inherently incompatible with operational control, because operational control requires there to be an agent who is able to directly causally influence the outcome of a system. But by definition, a fully autonomous system doesn't have these kind of agents, because it's fully autonomous. So this would entail that no one is responsible for fully autonomous systems, and this is very implausible, but because they're at least the constructor, the legislator, or the designer, they're people who are responsible, even if they are responsible in an indirect way. So this requires us to look at different conceptions. So tracking control is a possible conception that we can look at. But if we are not happy with that, we should try constructing different conceptions. And Giulio and Luciano will talk about a conception of control that has been constructed to fulfill the function of control best. So let me recap by this schematic overview. So how can we integrate this conceptual engineering? So when we're creating a value hierarchy, we identify a problematic concept, then we try to reverse engineer this concept by seeing what the current function is. Then we should do some moral theorizing, some ethical theorizing to see whether this is whether you can justify this function, whether it's a good function, and this is the normative function. And we can determine which of the rival conceptions is able to fulfill this function or construct a new function. And then we can fill in this new conception and continue creating the value hierarchy until we are done and end up with the proper design requirements. So this is what I wanted to say. I have a slide with references, and now I would like to invite Giulio to tell us more about meaningful human control.
Hello, everyone. So I'm Luciano Siebert. I'm an assistant professor also at the same university as Ivo at TU Delft. So I'm at the Intelligent System Department. So that's one of the computer science departments here. And I work broadly on the topic of trustworthy AI, responsible AI, and more specifically on understanding these questions of control in the design and development of new technologies, so especially AI-based technologies. So in this short talk, what I want to say, so there are two main goals here. One is I want to illustrate, give some views of what are the issues with responsibility attribution on AI systems. So for this throughout my talk, I'm going to use the example of automated vehicles, but I mean, they do apply for a different set of possible issues, possible scenarios there as well. So beyond automated vehicles as well. So we do have some work looking into, for example, the use of AI to support recruitment, also on energy systems. There's also on AI supported deliberation. There's quite a lot of, so these kind of things would also apply to these different domains in different forms. A second goal is to present one possible approach in which we did in order to try to get more concrete developments, to more concrete specifications and guidelines for design in engineers. So providing a little bit of context here, I mean, I'm sure that as you all work with emerging technologies, with AI, so I think you're very much aware of the societal ethical impacts that might be used of or if you just apply technologies there without proper consideration of the societal context or understanding of who is the group, who is using, what are the ethical considerations. So in So we make a little bit of a counterpoint here. If you look at basically, let's say 1990s, 2000 developments, there's a lot of this culture also in technology development of move fast and break things, just go there, try something out, put it on the market and go get better. But there's of course a big difference when we have like if the impact is some kind of like error for page not found or something like this, something very that is might be annoying but not necessarily harmful, depending of course on the context. What is this page about, of course? But so when we have limited capabilities of such systems in the terms of what they can do, so if they also require a lot of supervision, a lot of manual work on the background in order to deliver such a service, so the limited impact of when things go wrong are might not be that large. Of course, there are cases that might be a little bit different given the context here, but the more those kind of technologies, the AI system, they are capable of delivering good predictions, they're capable of perceiving the environment, and they're capable of interacting somehow with people. Think about all the way from the new all large language models, the use of AI for prediction, for hiring, for defining who would most likely commit crimes again or not, also all the way to the automated vehicle. So the impacts get bigger and more concerning. And so we did one study here to understand a little bit more about what is the problem also with responsibility, specifically in the case of automated vehicles. So I leave here the reference to our study here, if you're interested. So in a nutshell, basically we created some scenarios here in which a driver with an automated vehicle, so this is not done with a driver, we have a lot of research with driver experiments with vehicles, but this is more like some online vignettes in which we propose some scenarios in which the driver, for example, is not distracted, is distracted because of they have some intention behind this, so they decided like to read the news, for example, and unintentional send out like they are mind wandering because they are. So the car is driving in the road and the person is just supervising, but it is a very, very difficult task for people to be this supervisor and keep understanding of what is going on, keep an oversight of this. So, and then we ask a lot of people online about what in these different scenarios. So how do you see, so, and there was also another distinction was a short and long duration of these distractions. So how do you see the ability of people, so the ability of the people to intervene when necessary, the awareness they had in the environment, and then we also ask, what do you think is, would the person be responsible if some things go wrong? So basically the main outcomes here, so you can see that when we look into driver awareness here, we say, okay, if they are not distracted, they are more aware of the environment. If they are distracted, they are usually a little bit less aware of the environment. There's a perception here, and there's also the ability to take over. You see a little bit more, so let's say a trend at least, that the drivers are less able to intervene when needed. When there is a distraction, a little bit more longer distraction than short distractions, and also different patterns in terms of the distraction was unintentional or intentional. But I think when things get a little bit more interesting in a way, but worrisome in another way, was when we look at regarding to responsibility here. So the conclusion that we see also from this graph here is that a distracted driver is perceived to be less able to take control and avoid the crash. So people acknowledge that if persons are distracted because of their intentional or unintentional use, they are less likely to be able to avoid a situation when the vehicle would say, oh, I don't know what to do, please take over. And the person would be not aware, it would not possible to do this. Regardless, the driver is held primarily responsible for the outcome. So there's this kind of this tension here that humans, so you can see on the figure on the right-hand side here that even though they say that the ability might be on the lower gap, so here the shaded areas represent 70% of the points, the responsibility is still attributed to the user in most cases. So that's one scenario that when we look in the concepts of meaningful human control, which Giulio will also elaborate a lot further on where the concept comes from and what does that mean in the different from a philosophical perspective here. So I will focus more on the question of design and engineers. So how can humans be responsible for system design to function without or little human intervention? Or the flip side of the question is how we can design and engineer systems that can keep a possibility for proper understanding, attribution of control, and thus also of responsibility. On here, I'm going to connect here to these conditions which they have been previously proposed, the tracking condition and the tracing condition for meaningful human control. So again, Giulio will also touch on that topic and elaborate a little bit further. So I just take this as an initial case. So I think also following up with what Herman said about tracking this different understandings of control. The tracking condition says that for a system to be under meaningful human control, should respond to the relevant moral reasons of the relevant humans and the relevant factors in the environment in which the system operates. So basically, what it's saying is that the system should be able to track these moral reasons in a different set of contexts and for a different set of stakeholders. So if there is a change in these moral reasons due to an unexpected circumstance, due to new players entering the stage, the system should be able to track this in order to guarantee some form of meaningful human control. And the other condition is the tracing condition that says that for a system to be under meaningful human control, we claim that there is the possibility to always trace back the outcome of its operation to at least one human along the chain of design operation, so that we should also not just say that the system should be able to do all those things, but also that the outcome should also be traceable to to a human understanding. So myself, I have an engineering background. I'm working also with computer science, with AI development already for quite some time here. And when first I encountered this also through the AI Tech Initiative on Meaningful Human Control, which is an interdisciplinary program here at TU Delft focusing on this concept of meaningful human control. I must confess, I struggle a lot in the sense of, okay, what does that really mean in practice? So if I want to develop some system that has a little bit more of meaningful human control, what should I take into consideration? What should I do about it? So, and here on the remaining of my talk, I want to talk about some of this work we did into trying to get some more actionable properties for AI system development towards meaningful human control. So it's taking a starting point is tracking and tracing conditions. So this understanding of control as a form of guidance control, as put by John Fisher and Martin Revisa. And looking at this, so how do we do this from a development perspective? So here, in order to do this, we follow this process of abductive reasoning here. So basically, we look into meaningful human control broadly, we look at tracking and tracing the properties, and we look to a set of different cases. As I mentioned, I'm gonna due to time constraints, I'm gonna focus only on the automated vehicles, but we look at a set of possible cases in order to define this. So this work, of course, Herman is also one of the co-authors, was also involved in this project. And so one of the things we consider here that really struck for me is the relevant here, right? So we look into the relevant moral reasons, the relevant humans, and the relevant factors in the environment. We say, okay, in order for a system, it's quite tough also for a system or for a given implementation to define what would be relevant, what would be not relevant on this. And that's also a question. Maybe we don't want also to have this definition towards an AI system to define what is relevant, what's not relevant in this very sensitive context. This, we propose then the concept, so the concept of a moral operational design domain. So what is this concept of moral operational design domain? So we are getting some inspiration from the operational design domain. That's something also on the context of automated vehicles, which tell us what are the contextual conditions under which a driving automation system is designed to function. Let's say, for example, it's really focused on the technical and infrastructure conditions. Let's say this car would be able to operate with this degree of safety on highways, but maybe not in a city center of a busy city or a historical city center in a very crowded with a lot of different people walking around. So it would work on a sunny day, but maybe not if it's under heavy rain. So these kind of conditions are defined in an operational design domain. But what we claim is that the consideration of this wider societal implication is lacking. So then what we propose here is that moral consideration should also make part of this operational design domain. So we look here not only on design time, but also looking into operation time. So what are the set of constraints so that allow, so as we define this set of moral conditions here, we can, of course, give some kind of a possibility for either the system, also for the human, in order to keep track and try to understand what are the boundaries and constraints. So so moral ODD, of course, we acknowledge that this is also a very blurry line, which also gonna be quite dependent on a given understanding, a given definition. So that's also the connection also to conceptual engineering that becomes very important. And also this looking at this pluralistic also a way to understand this so that would align to different stakeholders. So one simple example just to illustrate what we see as the moral ODD. So there are some things that are, like say, as a simple tool, like a hammer. A hammer can do some things and cannot do some other things. For example, a hammer cannot be meaningfully used to destroy, to break down a huge building, but it can be used for construction work in a smaller scale. But there are things that the hammer ought to be used, for example, for construction, for maintenance jobs, but should not be used to hit someone. So that's those kind of considerations. What is the intended use and the moral, the acceptable use of these tools, they should also be part of this operational design domain. So, for example, here, when we're talking about automated vehicles, we can see, so if we have a clear somehow of a definition of what is the understanding of the safety, efficiency, or the personal freedom being some of the values behind the use of the automated vehicles that allows for some future traceability and future also reasoning about this. Of course, to set this up is also not an easy task at all. There will be a lot of tensions among different moral reason stakeholders, subjectivity, personal cultural difference on interpreting given reasons. So, and we have also in our paper, we elaborate a lot further on what will be some approaches. So here I'm just gonna give you the properties, the concepts involved that we are proposing. But of course, we do also try to connect this to some more concrete design in engineering practices here. So, but even if we define this more operational design domain, the things can change through time, through context, new stakeholders might also start interacting with the tool. This preference might change. So I think one important thing here, which we claim as well, is that to guarantee that some kind of proper moral understanding at all times that would allow there's a more acceptable attribution of responsibility is that humans and AI agents have some form of appropriate and mutually compatible representations of what is going on. That's the property 2 that we present here. So the system should understand, for example, in the case of our traded control, that if I'm going to trade over control to a human because the system is not able to do this, this should not have been done, for example, in just half a second. After someone you're just supervising the vehicle for 30 minutes and then you have half a second to intervene. You just cannot do this. So the perception of what is the ability of a person to do this is not aligned with those things. So that connects back to the illustrative example which I gave you about about automated vehicles and this misrepresentation of the abilities there to understand the responsibility and ability to take over here. For example, also understanding, are the safety thresholds, the guidelines shared or not? So that of course requires some continuous monitoring and update of what is the shared representation, what would that mean? So that gives them a layer to interpret what is the moral ODD or not in this given sense. However, even if you do your best in both cases as design engineers there, so things can still go wrong. There might be unexpected situations with more failure of the systems. So then we propose here the property tree that relevant humans and AI agents have ability and authority to control the system so that humans can act upon their responsibility. So that connects again to this question that ability should not be smaller than control authority, and control authority should not be smaller than the responsibility. So one thing is enabling the other one. So let's say in order to take responsibility for this, they must be able to do something about it. So let's say you're in an automated vehicle that has no steering wheels. There's nothing you can do to intervene. You can hardly make appropriate attribution of responsibility for the person inside the vehicle, and the same goes for the ability here. So and that's also not only the physical means to take control, to intervene, but also the ability to do this under which conditions and understanding this. So last but not least, we look into this a little bit more focus on the tracing condition here, is that actions are explicitly linked to decisions made by humans who are aware of their moral responsibility in this development. So we divide this into forward links and backward links. So forward links looking towards a forward responsibility. So humans within a system makes a decision with moral implications. Humans should be aware of their moral responsibility. What would be the implication of this? And when something happens, a given consequences, can we connect this back to a set of decisions? That could be a set of decisions by the operator, by regulators, by the manufacturer that would lead to this outcome here. For example, here, so that's also this explicit link is not only to any kind of decisions, but to decisions that allow some moral understanding, moral awareness. So consider a vehicle that slows down and pulls off the road after recognizing a given accident on the road. The vehicle also might need to remind the driver the duty to provide assistance to possible victims in the accident. So that's a little bit more towards the forward link. So of course, backward links in terms of accountability, also to provide explanations for these outcomes, but also forward, I just chose to provide this example on the forward links. So to conclude, I think that the properties I present, I think that we aim to serve as a more practical tool to bridge a little bit the gap between this kind of philosophical understandings and conditions of meaningful human control, a little bit more towards the practice, so becoming a little bit more actionable. But it's all at the same time we acknowledge that this designing for meaningful human control, it's definitely not something that can only be tackled from a technical perspective. It definitely needs transdisciplinary practices that incorporates multiple disciplines, and also that requires that this what we call design for emergence. So the understanding that this unexpected situations might arise, and the use of AI itself will influence the outcome of the system and behavior. And finally, also, it's important to say that meaningful human control is I see as one of the very important concepts that are being discussed here, but they are not a guarantee for ethical use of AI, because you could have something that's tracking and tracing conditions, but one might argue whether these conditions can be acceptable or not for a given audience. So that could be under meaningful human control, but not achieving the the appropriate reasons, not tracking the appropriate reasons. Thanks everyone talking before me. Set up a great stage, awesome, beautiful. My name is Giulio Mecacci. I am assistant professor of ethics of AI. I work at the Donders Institute for Brain Cognition and Behavior at the Radboud University in Nijmegen in the Netherlands. Yes. I want to talk to you about meaningful human control over AI. I'll go a little bit over what others have said, I am sure. But what are my aims today? Twofold. To present one possible approach to redesigning the concept of control to preserve responsibility in highly automated socio-technical systems. Well, it's been spoiled already. Meaningful human control is what we call meaningful human control. To present how, that's the second, that can have an impact on technical and institutional design, meaning, okay, what do we do with it? Can we do something? Give a little step towards, operationalizing, realizing something, designing. How? And it's going to be one or two examples, like going down a rabbit hole. It could be a little complicated. It's a teaser, okay? Bear with me. It's a teaser, 15 minutes. Probably, I hope I'll make it in 15 minutes. But, so what's the problem? What's the underlying issue? Responsibility gaps, and autonomy, right? Autonomous systems these days, they're invading us. In a way, everything is being automatized. AI is everywhere, and it's good. Not necessarily, but it can be really good, right? It's something that is desirable to automatize, to take away some boring tasks from us, and many different reasons. But more autonomy for many people means a sort of compromising over or lack or abandoning the idea of having human control. And with that, almost in a logical sense, right? If you're autonomous, then you're not under control, right? What the hell? But with the lack of control comes, or may, but I trust that, it comes an increasing difficulty in attributing responsibility and moral accountability to human agents, which is also something that we very much desire. So how do we get the cake and eat it? Can we, or do we have to compromise? Like, you have a certain space that you have on one hand, automation and innovation, and on the other hand, you have control and responsibility, and then you have to juggle, right? The more of one, the less of the other one. Now, what the idea, or what we strive for in the field with the concept of meaningful human control is to expand this, to sort of overcome this trade-off, to get us more to maybe have the cake and eat it a little bit as well. It's a new thing. Is that possible? Question. So what we saw is in the last 10 years, a little longer maybe even, in the context of autonomous weapon systems, this idea of meaningful human control formulated like this was born. And it was about integrating the notion of, the concept of control that Herman also explained very well in terms of, the classic notion of operational control. It's not sufficient. How do we integrate it to sort of have a satisfactory concept of control in those contexts where there's high stakes and very high levels of autonomy, such as autonomous weapon systems? So several actors started integrating the concept with a number of normative requirements. These requirements were about both the design of the system and the features, virtues, characteristics that a certain controller or designated controller would have needed to have in order to be deemed, genuinely, meaningfully in control of a certain technology. You see, don't even read this, but just as a few examples, Article 36 references to the need for predictable, reliable, and transparent technology. This is about the design, right? Requiring, Ibo already mentioned this way to go, right? The Department of Defense of the United States mentions the need for operators to make informed and appropriate decisions. That's about,
the operator, the user, the controller or controllers, certain features that they should have. So this was, and several did this, started integrating the classic operational notion with more requirements to make it meaningful in those cases where, simply sitting in front of the buttons room, right, and pushing the red button wouldn't make you genuinely responsible, neither in the forward sense nor in the backward sense of responsibility for the actions of an automated system. So when I started working in meaningful human control, I borrowed this notion of meaningful human control from Jeroen van den Hoven and Filippo Santoni de Seo. It was a two conditions philosophical account. And one condition is a little bit more metaphysical in a way, more abstract, and another condition is a bit more practical. These two conditions are called tracking and tracing conditions. They have been mentioned by Luciano already, and so it's going to make my life a little easier. The tracking condition is the more philosophical one. That's about reaching a certain attunement between humans' reasons to act, moral reasons to act, and the actions of an automated system that is, supposed to be under their control. And this is it's also called reason responsiveness. It comes from a philosophical tradition and free will, philosophy of action, and so on and so forth. But the idea is that there has to be an attunement, but a highly abstract attunement between, people's will and the technology's behavior. The tracing condition is more similar to the pink table that we saw in the previous slide. Well, you didn't read it, but that's fine. It's just it subdivides itself in a number of subconditions, but it's about the identifiability of a human agent in the chain of command. Right. So there has to be a human agent with certain right capacities. And, this condition is also long and developed. It's not this, it's much bigger. Plus, they have to be aware of their own role as moral responsible targets of moral blameworthiness, even for the actions of an autonomous system that will or may act on their behalf. So this is, these are bunch of requirements for the controllers on the human side. The tracking condition is, well, a little more mysterious. So what happened? Don't get scared, huh? Or do maybe. I started thinking at the time, how do we? Okay, this is really nice. It's good to it's very convincing. But how do we make this highly abstract notion of, you're in control when the technology sort of is compatible with is aligned with your reasons to act, moral reasons to act? How do we make it tangible? How do we make it workable? There has to be we have to trickle down the line and make it applicable. So I was working at autonomous driving systems. That was me. Autonomous driving systems in traffic. I was working with traffic engineers. I was working with traffic psychologists. And I knew one thing. I knew that a very common, very widely used, very popular concept of control, theory of control, was that of Jean Michon, a traffic psychologist, very popular. He had this just tripartite sort of theory that would deem that was about cars. It is about cars, drivers, and their control over cars. And he divided control into three levels. The operational level, that's like basic actions, maneuvers, like, overtaking, and plans, more abstract. Okay, so simplifying, a system would be a car in this case, would be under control of its driver if it responds to these these three levels of description of control, to the plans, to the maneuvers and the operations of a driver. Now, I also knew that that was what the engineering could already sort of manipulate, could work with. But there was a striking resemblance with certain sections and branches of the philosophy of actions, in particular practical reasoning, where for instance, Bradman would talk about, would mention this principle of proximity, right? Which is sort of the level of granularity that was used by Michon in operations, maneuvers, and plans. He was talking about proximal intentions, which would correspond roughly, or we argued that it would correspond to operational control. But there were distal intentions. They were talking, these people, they were talking about reasons, right? They were talking about the things that the tracking condition was talking about. But there was more. What I realized was that the philosophy of action, once you found a map to translate it into what was the concept that were already out there and used, was more encompassing. In fact, Raz 1975 includes in the reasons that control a user's a person's actions. We made it actions of the machines, but that's it's complicated. There's some space in translation, but they included the author included values and norms into the field of things that would, the reasons that would boil into what influences a system's behavior, a person's behavior. That was really important because it went exactly right down the alley of meaningful human control, of the tracking condition that is there. Because of course, in an automated system, you have an abstract, more distal relation between a controller and the actions of a system. This was explained very finely by Herman already. So in a way, we could find a way to conceptualize values and norms and the bearers of these values and norms as being in control over certain behavior of an automated system. So to encompass more users, more scary stuff, a big arrow. So this is what we did to put together the concept coming, from philosophy of action and those that were coming from traffic psychology. I proposed this proximity scale using the proximity principle, how distant in time, space, an actor is towards the system. As already explained, thank you, Herman, actually. The proximity scale is sort of the human reasons here are ordered in with respect to how closely they influence a system's behavior. And this scale is sort of a reference framework that is configured as a continuous space, okay? The relevant aspect here is the reasons relative positions, but you can identify classes, which is important. Classes of reasons can be identified. Why do you want to do this? Intentions, plans, values, norms. Why do you want to do this? Because this is useful as it contributes to identify different classes of agents and that are typical bearers of those reasons. So you're sort of you're putting down a scale. You have a reference framework to understand the different reasons and the different actors that may influence the behavior of the system. And again, you're asking, what do you do with this? It's still very conceptual. Can you do this? Can I do something with it? I hope so. Last slide. This is a bit more complicated, but I want to tease you into believing that there's something actually practical to do with this. In this slide here, you see what we did. This is 2023. What we practically did with this is a very simple governance algorithm that sort of grants a way to decide what, in the space of the many concurrent reasons, that it can be identified in a situation. This situation is urban traffic, in particular, how certain automated device, say a self-driving car, should behave, which is in our language, what type of reasons it should respond to. It's arbitrary. It's not. I mean, this is a model of what could be desirable in a certain societal context. It's not meant to be absolute. But you see here that I identified arbitrarily 4 levels in this partially automated driving scenario. They can be as many as one requires. It doesn't, you don't need them to be 4. A rule states underneath, using the notion of proximity, that a system should respond to the most proximal level that complies with all the more distal levels, which also satisfy this condition. I'll make an example. Don't sweat it too much. The system should respond to the reasons of then lower levels until those reasons don't conflict with reasons of a superior level. This is a similar structure that you can find in certain legal systems, for instance, the relationship between constitution and the different codes. And so, for instance, and then I'm concluding, in this example here, I sort of decided to give priority to the interests, the reasons, to act of the most proximal levels. Though level 1 and level 2, like in terms of proximality, they're the same, but we wanted to privilege, indeed, for safety, especially vulnerable road users. In this case, if a pedestrian, let's say we're at the zebra crossing, that's the example, automated vehicles will need to stop. This is also in case, though, the driver does not want to stop and give the way to the pedestrian. The driver's reasons with this algorithm, what it suggests is that are overridden by the interests, the reasons of a lower level. And since the driver's interests are not compatible with the higher levels, say the traffic regulations system, will refuse to respond or to be controlled by the reasons of the driver and give way to the vulnerable road user. I'll leave the conclusions to you because I'm over time. I do believe, I don't know, but I trust Ibo. Thank you so much.